Thomas Burns from Australia, and actually from the Okinawa OIST in Japan. Tom holds degrees in science and bioethics from Monash University, Australia, and will soon graduate from his PhD at the Okinawa Institute of Science and Technology in Japan. His research focuses on computational and theoretical techniques for analysis and modeling of neural and AI systems. He is particularly interested in representational structures of task and cognition, as well as computation with and dysfunction of inhibitory neurons and setwise neural connectivity. Well, thanks so much, Thomas, for joining us from all the way to in Japan, and very looking forward to your talk. So yeah, whenever you're ready. Thank you.
Sure. Yeah, thank you for the kind introduction, and thank you for having me. I'm really excited to tell you about some of the lush rainforest that is topology and geometry, and how you might be able to find it useful in your work. There is a lot of math forthcoming. I encourage you to interrupt me at any point if there's something that doesn't make sense to you. I encourage questions about anything, in fact, at any point. If you'd like to get in touch with me after this talk, the best way is via Twitter. My Twitter handle is at the bottom of this slide. And all of this work is not possible at all without my collaborator, Robert Tang, who's now assistant professor in China. And we're still working on some of these topics. And if you're interested or inspired or curious, please get in contact with either of us. We'd love to collaborate further. So the title of this talk is multi-agent navigation and a social place cell hypothesis, which I'll give towards the end. First of all, do you think that an autonomous vehicle? I'm gonna mute the sound on my laptop. Can you think of an autonomous vehicle that could navigate this intersection? I doubt that could, and I think possibly one. Oops. Oh, okay, it's missing the little pop-ups. One response that a machine learner would tell you would be, oh, well, we just need more data, don't we? We need to train it in these more complicated situations. But I think the sort of geometric perspective or topological perspective that I hold, and I'll speak a little bit for my collaborator here and say that I think we have a vision where you could already know how to navigate this environment if you knew some of the simple rules that are going on that may be already present in the sort of more structured, cleaner, sort of less complicated intersection that you might find somewhere else. And then let's look at this little video. These are beautiful natural phenomena. This is a flock of birds, and it's called a murmuration. You can see this wonderful undulating patterns that they exhibit. And statistical physicists and neuroscientists, ecologists, they'll talk about these local rules that generate these global patterns and phenomena. And indeed, that's probably a very good explanation. But oftentimes they have a sort of statistical flavor, a sort of probabilistic flavor, not necessarily a very deterministic flavor. And yet it obviously is partly determined by these local geometric and topological sort of structures, these sort of relationships between the agents. And again, from a more geometric and topological perspective, we want to talk about and think about how can we deduce those given some data, for example. Okay, so I'm going to unmute now so I can actually hear you now if you talk to me. Sorry if anyone was trying to talk to me just before. This work has already been put on archive and already talked about at a workshop in iClear last year. A grid world is a two-dimensional flat array of cells arranged in a grid. Like on the right here, I have a 3x3 grid world, and you can see there's a koala that's going to be our agent throughout this talk, and there's also this beach ball that's going to be the object throughout this talk. And these are really just labels of the cells. These other labels here exist, and they're the empty label. So cells can be occupied by, say, an agent or an object, or it can be unoccupied. And you might say, Tom, that is such a simple system. Why would you study grid worlds? Well, first of all, because they're so simple, we can scale them, and we can develop and test very large algorithms, very large data sets. Also, you can make it more complicated. You can add rewards and punishments and drop bears, if anyone knows what a drop bear is, and lots of fun and exciting things. It's like a sort of discretized 2D video game. And also to the extent that you can make it more complicated, you can sort of analogize real world scenarios. For example, you can look at navigation, maybe, for example, logistics in an Amazon warehouse, or indeed self-driving cars and that sort of thing. And in particular, what I like about it is it provides a formal setting for us to specify a range of problems. And today I'm going to be talking about multi-agent navigation and collision detection. So we use a framework called reconfigurable systems, and this is due to three mathematicians, Abrams, Ghrist, and Peterson. And informally, we have the following. We have a graph, G, and we have a set of labels on that graph. So this graph is the grid world. It's actually the jewel of the grid world. It just means you put a vertex in each of those cells, and then you connect them up depending on which sort of cells are adjacent or glued to the other cells. And the labels are the agent, the object, and the empty. And then we have some states. The states are labelings, A, on the vertices of G. So that's kind of just what I said in different words. And then we have some generators. These generators locally relabel the states, and I'll explain that through this example. This is a 1x5 grid world. It's 1x5 because it's sort of just a single corridor of width 1 and length 5. And you can see here, here's the koala, here's the object, here's empty, empty, empty. And they've drawn this line. That's an edge going to this next state here. So these are all different states here in this staircase structure. And where we have an orange edge, we are using the generator called push-pull. That's this relabeling. So whenever we see this little local subgraph, we relabel it to this little local subgraph. So you can see that goes koala ball empty into empty ball, empty koala ball. And it's reversible as well. This is an undirected edge, so we can go forwards and backwards. So that means if we're at this state, we get to this state by applying that generator. So you can see these three little cells here become these three little cells here by applying that generator. And then if we go up, for example, here, we're applying the move generator. This is this sort of maroon edge here, and you can see the koala just jumps across to the adjacent empty square. Like I said, this graph is the jewel of the grid world. The labels formally are agent, object, floor. And this staircase structure falls out, which is quite natural and nice. And you can easily see for yourself that if you add one extra cell here, an empty cell, what will happen to this structure? Well, it will just extend the staircase by one step. So let me just formalize this generator idea. So we denote this as phi, and it comprises the following. So it has a support of the graph G, and remember the graph G is just the jewel of the labeled jewel of the grid world, and this is called the support. And then we technically have another subgraph of this subgraph, which is called the trace. And then we have an unordered pair of local states, the sort of the relabelings, U0 and U1, where they agree on the support, but they disagree on the trace. So it means that you can define a generator where you consider sort of like some sort of pattern match that you find, and then within that, or potentially all of that, you relabel. And the stuff that you relabel in that sort of pattern match is the trace, that the pattern match itself is the support. And those changes that you make are called the local states, and there are just two of them. You change one to the other. And so we say that a generator phi is admissible at some state if we're in one of those local labelings. And if that holds, then we can apply phi, and you obtain the new state by applying it and relabeling those vertices in the trace, and then everything else stays the same. And notice if you apply this twice, you just get back to where you started. Here's a more interesting example, a 3x3 grid world, where instead of drawing the whole grid world in each of these little states, I'm just highlighting the state that we're at in this shaded vertex and then drawing that state on the right. You can see this nice sort of flower petal arrangement shows up. You can see as well that there are these different colors at the edges. The orange one is the push-pull generator, and the darker one is the move generator. And if I just pause it and rotate, and then also add some circles, topologically circles, they're sort of ovals, some of them, around different clusters of states, you'll notice that there's a sort of new scale of geometry that you can look at, or at least there are two scales. The broader scale that I've sort of clumped these clusters, these clustered states together with, within them all have the move generator present. But to go from one of these clusters to the other is the move generator. And so you notice as well that there are 9 of these arranged in a 3x3 grid. What are they? Those are the locations where the ball is static. And I've arranged this, rotated it, so that this cluster here represents where this ball is here. So this is the current state. And we can know just by this representation that, for example, this state here must be that the koala moves here. Why that must be is because in order to get into this state, which is sort of aligned with this grid, we must be pushing the ball down into here. And the only way to push this ball down into here by moving only one step of a move is to move to here. Also, too, this state here must be that the koala moves down here, because that's the only way that you could then pull the object into the center. So these reconfigurable systems generate what you've been seeing, and that thing that you see is called a state graph. And these are probably familiar to most machine learners. If you think about a reconfigurable system in this system, then again, you sort of have this graph G, that's the tool of the grid world, and you have the set of labels. And these labels can be anything. You know, I'm just giving you an example here. You can use this in many different systems. And what we just say is formally this set of states is closed under the action of taking this will generate. So you start with some state, and then you take all possible generators, and then you do that iteratively using a breadth first search in our case. And then we finally find all the possible states and then link them up according to those that are linking together by the generators, which is what I say here. The state graph S1 is associated to the reconfigurable system and has vertices as the states, and edges connect pairs of states which differ by a single generator. Okay, but actually we can go further than that. We can go higher dimensional. And specifically, we can think about state complexes. This is a state complex. Why is it a complex? Well, you notice here that we have some sort of red shading here and here, not here and not anywhere else. Those shadings topologically represent a square. They span 1, 2, 3, 4 vertices in both cases. And they're a new sort of high dimensional generalization that we're putting atop the state graph. We're making it into a complex. And specifically, we're making it into a cube complex. I'm going to talk more about that. In this example, we're putting these squares in when we have a 2x2 grid world in this example, and we put them in when there's commuting moves. So what does a commuting move mean? Well, let's look at this cycle here, this 4 cycle, since it has one of these squares, right? When we move from this state to this state, this koala moves up. And then when we move to this state here, this koala on the left moves down. Then we move to this state, the right koala moves down, and then we move to this state and the left koala moves up. So what happened was that these 2 koalas are just kind of like sliding past each other, just, you know, not touching each other, not stepping on the other one's toes. They're just doing their own little thing. That means that if we wanted to go from, say, this top state to this bottom state, we could sort of think about it like it doesn't matter if we do this move and then that move, or if we do this move and then that move. The order doesn't matter. So therefore, we can do them both at the same time. They also sort of don't interfere with each other. And more formally, their supports do not intersect. In our case, the supports and the traces of the generators are the same. And the same is here on the right, except they're just moving horizontally. Why don't we fill this one in the middle or any other 4 cycle, for example? Well, that's because they are topologically non-trivial. Here's an example in the center cycle. So if we go from this state to this state, the bottommost koala moved to the left, and then we've moved here, the topmost moved to the right. And now the top one goes down, and now the top one, the one on the left goes up. So what happened with these 2 koalas actually did like a half twist. And then if you do 2, they do a full rotation. So there's actually some braiding of the agents. This makes it topologically non-trivial, and therefore we fill it in. Whereas here, you have agents just moving around next to each other. They're not braiding, they're not mixing. So they're topologically trivial. So we have these commuting generators, and when we have those commuting generators, we say that they that we can put a square there, or an n cube more specifically. So, and that makes it a state complex. So a set of admissible generators, 1 to n, at some state s commutes when they can be applied independently of one another without affecting one another. Remind me tomorrow. Oh, we lost our spot. Sorry, everyone. I'll resume slideshow. Okay. And yeah, so we can apply them independently and without affecting one another, and that results in that the resulting state does not depend on the order in which they're applied. So the state complex S of a reconfigurable system is you start with S1, state graph, and then you start adding in these n cubes whenever there's a set of 2n states which are related by this set n of admissible commuting generators. This leads to some interesting symmetries. For example, this grid world here and this grid world here share exactly the same state complex, and yet they have opposite numbers. Well, yeah, I'm going to give it away. They have an opposite number in some sense of opposite number of agents, and this state here, this shaded vertex, is exactly the state of these two. Why is that? Well, the reason is because this object doesn't care about the identity of the labels. It just cares about the dynamics of the geometry. Like the sort of, it's capturing topologically and geometrically the dynamics. It doesn't care about specifically what you as a human choose to call that dynamic or that dynamic. It just cares about the dynamics. And in this case, you can just simply invert the labels and you find that you get exactly the same dynamics going on. I just want to check that my connection is okay and that you're all still with me. Is that good? Could someone just give me
loud and clear?
Loud and clear. Okay, great. I just was checking. Great. So let me continue on. All right. Now I mentioned state complexes are cube complexes. Specifically, we're making a cube complex. What is a cube complex? A cube complex has cubes in it. It's a thing that's made up of n cubes. And if you generalize an n cube, a cube in general, you can think of it as, well, at the 0 dimension, you have points. At the first dimension, you have lines. At the second dimension, you have squares. And then, you have a 3 cube, you have lots of things, and you glue them all together, a bit like Lego or something. Not like Lego, but, some kind of child's blocks kind of toy thing. And each face, in this case, for example, point, line, square, and so on, that's an elementary cube. And if that is in, if we have, for example, this square, then we must have all of its faces. That means sort of its lower dimensional stuff. So if we have this square, it means we have the vertices that span it. We have the edges that go on the sides. And then, for example, this second condition here is the non-empty intersection of two elements can share faces. So, for example, these two squares share this edge and also share these two vertices. Those are both faces. Well, all three of those are faces. Now, specifically, state complexes, as I've described so far, are something called non-positively curved, that's NPC, cube complexes. And geometric group theorists get very excited about this quality. And let me explain why. First of all, this isn't a result of ours. This is Abrams, Ghrist Peterson. And they show that the state complex of any locally finite reconfigurable system is a non-positively curved cube complex. And the significance of this and why it's very special goes into some cat-zero geometry, which is not trivial, and I'm not going to explain all of it, but algorithmically, it's very nice for computing shortest paths, geodesics. So let me give an example. Let's say you want to go from this state here to this state here. How would you do that? Well, in a reinforcement learning system environment, you might reward this particular state, this particular labeling, and then you sort of iterate and give lots of examples, and let the sort of value for different states be learned, and hopefully you, with some Q function and so on, value function, you learn the dynamics that lead you to that particular state. But it's quite specific, right? You have to train, you have to specify which states ahead of time that you want to go to, and so on. Well, if we think about it with our system of cube complexes, specifically non-positively curved cube complexes, what we're really saying is we want to go from this state here to this state here, and we want the geodesic, the shortest path. It turns out if this is non-positively curved, you don't need to compute the whole thing. You only need some local information, and then to know the labeling here of this other state. And then on top of that, you just need some local information, which you can gather from your little neighborhood. And then you have basically a list of things that you need to sort of cross off the list. And these features are called hyperplanes. Hyperplanes, basically the hyperplane structure of non-positively curved cube complexes performs or is structured in a very nice way, which is what allows this algorithm. And you just cross off your list, and you're guaranteed that once you cross one of these hyperplanes, you don't have to go back and cross it again. And what's more is you're also guaranteed that whenever you approach a new state, there'll be at least one of these hyperplanes that you can cross. And once you've crossed all of them, you'll be at the state that you want to be at. So it's an extremely efficient algorithm, which is local, doesn't require to compute everything, and you can just go to wherever you want without even knowing really how to get there or the global structure. Now, how do we check if something is non-positively curved? And we're talking about cube complexes here. Well, I'm going to give an intuition, and then we're going to give the technical detail, although not all of it. So think of the following two kind of box cube-like things: a solid block of cheese and a hollow box. What happens if I cut that corner in this kind of fashion, like diagonally? Well, what's the cross section? In the solid block of cheese, I'm going to get like a triangle structure. So if I cut the corner off and then I'm facing the sort of inside of this and looking at, it's going to be a solid triangle. Whereas the hollow box is going to be an empty triangle, right? And this is the intuition. Basically, the hollow box, if we cut the cube complex and we find a hollow sort of triangle like this, then that means that it's positively curved. Whereas if we find a solid block, then it's non-positively curved. So in particular, Gromov's link condition is that any finite dimensional cube complex is non-positively curved if and only if the link of every vertex is a flag simplicial complex. A flag simplicial complex is something like this. It's a filled-in triangle, you could say. We have the outline of a triangle, and we also have the interior of the triangle. Simplicial complexes, if you weren't familiar, are completely analogous to cube complexes, but instead of squares and n cubes, we have triangles and tetrahedra and high-dimensional analogs. Those high-dimensional analogs, instead of n cubes, are n simplices. Singular is simplex. And a simplicial complex is flag when there are no missing simplices. Let's give an example. This is a cube complex here, in gray, and then I'm pointing to some vertex here in the middle. And then this red circle is the sort of little neighborhood that we're cutting out, a bit like when we're doing that cut on the diagonal of those cubes. And when we do that, we can create a simplicial complex. This is called the link of that vertex. And the vertices here indicate the admissible generators. Those are the edges, basically, since those edges represent going from one state to another state in our system. And then the simplices, for example, these squares here, indicate sets of commuting moves, right? And so then in the simplex, in the simplicial complex, we add one simplices, which are edges, connecting the states which commute. So this state going up and to the right, both commute. Therefore, this is the up and to the right, and they both commute. So we draw this edge here. This is the null curvature example. Here's negative curvature example. You can see again, we have a similar sort of scenario where we're not outlining a triangle, and therefore these are flag simplicial complexes. However, when you have positive curvature, you have this problem. you have an empty triangle in the middle, that means there's a missing simplex. That means the curvature is positive. Now, this is all nice and well. Okay, so what have I said so far? I've said basically that we can apply the Abrams Ghrist Peterson reconfigurable system setup to Gridworlds. That gives us a nice way of finding geodesics, of representing the dynamics, and so on. But there's one sort of nitpick that Robert and I had, and that was that there was some uninteresting topology and sort of some just wrong topology that was going on. And in particular, it was this. If you have just a 2x2 grid world with a single agent, this is going to be the state complex under the original definition of Abrams Ghrist Peterson. And you might say, oh, that's fine. Yeah, it's representing the dynamics, and that's what it should do. But there is a problem, and that is this hole here in the middle. This is a topologically hole. And you might remember from earlier, a topological hole should be sort of topologically interesting, right? This is not interesting at all. If you think about it from a braiding perspective, for example, there is nothing happening. Or we're implying that basically there is something blocking the path, blocking the way for this koala to move from here to here, or that the order matters. Well, no, that's not true either. None of that is true. We're really working on some discretized 2D plane, and the only reason that this hole arises, this uninteresting topology, is exactly due to the discretization. So we say no, be gone. We are going to fill you in, and this is now going to be a square. So whenever we see this, we call it a 4-step dance with a single agent, we fill it in with this dance square colored in blue. The other squares that you'll see due to the commuting moves or the high dimensional stuff are colored, I think, in red in the subsequent slides. So we call this Dancing with Myself after a song you might remember from the 80s if you're old enough. And a dance delta comprises the following data. We have a support, which is this 2x2 subgrid that I showed you in the previous slide. The 4 local states, again, exactly 1 agent and 3 floor labels or empty labels. And then the move generators, which are connecting them. So just kind of like on that slide before. And then we say that it's admissible, this dance is admissible if we're in one of those local states. And then we introduce the modified state complex. And this S prime modified state complex is exactly like we were before, except now we start to add in commuting moves or dances. So specifically, whenever there's a set of 2 to the L plus 2M states, which are related by commuting set of L generators and M dances, we can add in an N cube, which has having the given set of states as its vertices and where N is equal to L plus 2M. Interesting topology remains in these examples. There's no way to fill in stuff here and remove the interesting topology that we started with. However, Gromov's link condition can start to fail. Consider these 2 examples. If we're in this particular state, right, then what are the generators available to us? Well, this koala can move here and here. This koala can move here. And then because of the dance, this generator exists as well, delta 1. Now, if we think about delta 1 as a sort of commuting move, that means it should be represented in the link as a 1 simplex, whereas these individual moves here should be 0 simplices or points. And that's exactly what we get. And you notice that 1 and 3 are connected because, well, 1 and 3 could happen at the same time. Those commute. Also, 2 and 3 are connected. They have a 1 simplex connecting them because they also could commute. But because of this dance now, we have a problem. The dance cannot commute with phi 3. And then we have it because we have overlapping or intersecting supports and traces. Therefore, there's no interior to this triangle, and then you have a problem. This is not a flag simplicial complex. You have positive curvature at this location in this state. Here's another example. Here, everything works except for at the higher dimension. So now we get a tetrahedra where it has a void in the middle. It's not completely full. It's kind of like the hollow box from earlier. And then we get positive curvature. Now, we proved that actually these are the only two cases where positive curvature can arrive in our modified state complex in an agent-only grid world. And it's satisfied, the Gromov's link condition is satisfied if and only if there are no empty 2 simplices or 3 simplices. And actually, you don't have to go through all of those kind of long-winded mathematical kind of calculations or computations, because it turns out actually it's really comes down to whether or not those agents are separated by a knight move or a 2-step bishop move. Here, these two are separated by a knight move in chess. These ones are separated by a 2-step bishop move in chess. Now, if I show you this, it's a 2x3 grid world, you'll notice that there are obviously, without even looking at these complexes, you can already tell there's going to be positive curvature just exactly at this state because, well, there's a knight move, there's a knight move, switch them into their other places, they've got another 2 knight moves as well. Here's the full state complex, and in blue shaded the dances here separately, and here the commuting moves. So this is the original state complex of Abrams, Ghrist Peterson. This is our modified state complex. And then you see situations like this one where there's failure. There's going to be more failure, I'm sure. Anyway, you see that there can be many potentials for failure. Are they going to do it? It's a random walk. So oh, there's failure, right? And then another failure when they were diagonally opposite corners. Now, instead of doing lots of examples and just, oh, there's failure, we did some statistics, and we did it with a 3x3 grid world just for sort of expository purposes. And you can see here in the leftmost column, we have a 3x3 grid world with an increasing number of agents. Now, if you have 0 agents, what's there to do? There's only one state, and it's, of course, non-positively curved, this state. There are no dances, no commuting moves, and we don't have to worry about any of Gromov's link conditions failures, the total number of failures, or the mean number of failures per vertex, or the maximum of any vertex. Whereas if you add in one agent, well, you're going to have 9 states, right? It's actually just going to be a dual of the grid world. And you're going to have 4 dances, right? Because there are 4 possible spots where you could do a dance. Now, if you look at the commuting moves column, you notice that it's symmetric about 4.5 agents. And actually, you should already remember that because I showed you the example of 3 and 6 agents being symmetric, right? And that's because you have the label inversion. What's interesting is you also get a symmetry about 3.5 agents for the dances. I haven't actually figured out why that is, but it's interesting, and it's notable that it shifted down. And that's kind of intuitive. Well, you know, you can't dance if there are too many people crowding the dance floor, right? And here the number of states. Oh, yes?
Sorry to interrupt you. I just had a question concerning the failure. What you call the failure is when you, like, the agent tries to an action and cannot transition to the next state, to a different state. One of the agent cannot move, basically?
Exactly, yeah. Failure in this case you can interpret as an instance of collision if those agents were allowed to do that.
But including also the edges of the world.
Sorry, the edges of the...
Including the edges of the grid world as well.
So in other words, it's like the way that we construct these things here, we're never actually allowing, because it's never possible in our system for these agents to collide with one another. However, when they're in certain orientations or sort of when they're in relative positions, in certain relative positions, they're at risk, according to the generators that we specify, of colliding if they were both allowed to do all of their movements. So this causes us to sort of notice that basically with this system, we can detect collisions or potential collisions using positive curvature, but we never actually allow them to collide because that's not possible in our system.
But then, like, yes, I see, for example, it gets one of the koala gets stuck in the top left corner at some point for a few time steps. Yeah. So that would be a failure as well, right? Because he's unable to move. He's trying to move, he's unable to.
Yeah, I mean, this is just a random walk on our representation, but basically the sort of the core sort of spiritual message of this is that, well, if you represent these dynamics in a particular way, which is true to the underlying space and is topological and geometric in flavor, as we're doing. We're using some geometric and topological methods. When you do all that, you end up finding that by removing a topological sort of defect in one place, you end up generating a topological, geometric detector in another place, which in this case is detecting danger or potential collisions. So we think that using structures like this and techniques like this, we can potentially detect through looking at the representation, not through any learning, just purely in the representation itself, we can detect task relevant features.
Yeah, that makes sense. Yeah, thanks.
No problem. And sort of, yeah, in further to that sort of line about, you know, what are these condition failures, these Gromov's link condition failures? Well, here we sort of show some statistics for that. The total number of failures is highest when you have 4 agents. So that is the sort of the most, you can think of that as like the situation where we have the most dangerous possible kind of control system. Oh, sorry, not control system, but, you know, the most dangerous situation basically for these little agents, and maybe the more careful we should make our control system in order to be safe. But and this also has the largest number of failures per vertex. What's interesting though is actually 3 agents where you have the worst possible state where there's lots of potential collisions. And of course, if you have very few agents or quite a few agents, then somehow the dynamics become less dangerous, basically, because there's less room to move around. So what are some applications of this? Well, first of all, positive curvature in our system indicates that there are some available moves which we cannot do or safely do independently or safely without risking these collisions. So there's also something in here about distributed cognition and compared to central control. And our theorem also you can interpret as saying, well, we need to just look ahead with a certain amount of foresight, specifically 4 moves, to avoid these collisions. And you could formalize that in many other scenarios, right? And in general, we hope that this basically helps researchers study safety and navigation in these sort of learning systems, which could then detect and prevent these collisions and or provide further coordination between the agents. And we think that there's actually a lot more geometric and topological information embedded in these kind of structures or modifications thereof, and we could use those to improve learning algorithms in such environments using that representation. And directly from that representation, we already have a lot of task relevant information. Now, one thing we've also been thinking about is, do neural networks already have a representation like this? And to do that, to sort of trial that, we looked at the following. We started with this kind of state, and we put it through a little multi-layer perceptron, and then we asked the network to predict the next state. Now, it should be a third here, because this koala is the agent that can move. The object can't, the beach ball doesn't move on its own, and you can only move in 3 different directions here. And then what we did after learning, after training, we looked at the activity of the hidden layer, the second hidden layer, and then and that has 50 neurons. And then we reduced that using PCA to 2 dimensions, and then we're going to study what's the geometric or topological structure of the activity in those 2 dimensions. Now, why is that even worth doing? Let me show you from the perspective of MNIST with the same network. If we put an 8 into this network, and again we get the same, we do the same thing. We look at the hidden layer and we reduce the dimensions. And then if we throw lots of different tests through this network and collect these vectors and do the dimensionality reduction, we get a plot a little bit like this. It's color coded here for the different class labels, and you can see 8 is right here in the middle. And that makes perfect sense geometrically. Why? Because you can think of this as analogous to the reason why everything lights up on the 8 in an LCD. Whereas when you move away from the center, you're sort of deleting things, right? You're taking away stuff in this algebra. So actually, you can see that there's a geometric reason for 8 being at the center of this hidden representation space. But what's the internal representation space of these grid world dynamics? Okay, we're going to do something extremely basic and boring. It's just one agent in a 3x3 grid world. Here are the points that show up if you do this. Of course, it's very boring. It's just going to be 9 different possible states, right? But we don't really see much of a pattern here. So what we do is we consider this as one state, and then we move forward in the dynamics, right? We go to the next state, and then when we do that, we get to 3 possible states, and we color those, and then we draw these edges, and I've drawn them for all here because we do it for all of them. And then after that, you sort of have these lines, these edges, basically connecting the vertices, the states, with the different set of dynamics. So this doesn't also look too good, but if we consider it as a graph, well, we're allowed to label the vertices, and then we can rearrange it, and you can find it's a jewel of the grid world. So it's exactly what you'd expect. What's more is the stuff on the right, so the positive domain of PC1, it's actually those that are on the side. On the left here, it's the corners, and also E, which is in the middle. It's a bit of an anomaly, E. And then you also notice that, for example, in this sort of Cartesian format that I've drawn this, you notice that local pairs obey some sort of Cartesian height, let's say, on the PC2, the principal component 2. So for example, H is ever so slightly above G, and H is indeed above G in this drawing here. B is above C, so is B above C here, and that follows, except for E, which is an outlier. So this is connected, I think, very, very non-trivially and quite abstractly to social place cells. If you know what these are kind of like place cells in the hippocampus, except they represent the space of another, specifically a conspecific, that is like another member of my species. And if I'm this orange rat, and I see the blue rat running around, there's going to be a little neuron that is active when the blue rat is in this location and this location. This is the heat map, basically. Those are the locations that this particular social place cell will be active when the blue rat is there. But when I'm the orange rat and I run, my representation in this little cell is actually going to be here, and then ever so slightly here as well. So it's slightly different representation. Here it is for bats. Again, I'm the orange bat, and I'm looking at the blue bat. When the blue bat flies, it's mostly this area, but when I fly, it's mostly this area. So what's interesting in both of these cases, it's sort of like looking a little bit forward in some sort of vector of typical activity. In both of these cases, this is sort of a very simple activity, but that's kind of what we do in science. We make things simple to see the patterns. What's interesting is there are also these self-dependent and self-independent social place cells. So on the left, we have the self-dependent, and on the right, we have the self-independent. Let's look at the difference. So here, the orange rat, it's sort of just always this representation, and then it's kind of looking ahead. When the blue rat goes onto the opposite side, it's following on the right side, it's following. Whereas the self-independent, it's kind of choosing to represent this cell is choosing to represent which side it goes to. But for the blue rat that it looks at, it's always the same side. Now, I think that this forms a very strong hypothesis for saying that this representation that we're thinking about is actually a basis for thinking about social place cells as egocentric. So we're thinking about from the perspective of one animal, one agent to another agent. They're vector-based because they care about the direction of motion. They're social because, well, of course, we're working with multiple agents or multiple animals here, and that they care about the place. And this in particular could be used I think, as a basis for collision avoidance between these animals. And here's an example of that at a larger scale. Here you can see basically these different cells, which are slowly coming from the border into the center, and then finally sort of scattered throughout. And maybe I go into this and at the end if people want more information. But basically, this is a hypothesis that I'm putting forward. This data is from a paper, and I think that theoretically these types of cells could be the basis for detecting collision and avoiding collision between agents, similar to our proof. So the take-home messages here are that purely geometric and topological features can capture some really non-trivial task information. In this case, collision detection. It's not actually easy. And furthermore, these features seem to be represented or can be represented in learning systems. And also, these social place cells, as I mentioned, could form a basis for fairly interesting coordination. And indeed, they would seem to be a natural home for the basis of such coordination between animals and between agents. And furthermore, I think that their coordination and their dynamics and interactions should have some intrinsic geometric and topological features which are not dissimilar from what we've shown. In the future, we are quite interested in looking at more types of grid worlds, more types of systems, self-driving cars or robots or whatever, through this framework, and looking at more labels and generators and filling in different cubes or cells. We're also interested in sort of some more mathematical questions and how those mathematical features might relate to different features of the, say, multi-agent grid worlds or whatever other system. Looking at optimization algorithms, geodesics, congestion and failure braiding. Another more mathematical question is like, is the n-strand braid group, is this a classifying space for the n-strand braid group? That sort of thing. Now, our software is open source. You can download it now. It's not while stocks last. It's just there on GitHub, and it's got a GUI where you can specify a grid world with different agents and objects in this nice sort of visual way, and then click create and save grid world, and then run another script, and it'll spit out the state complex and the links, and construct all the stuff to tell you about whether or not this is a non-positively curved grid world. So thank you. I will take any questions now, and I'll also just mention no koalas were harmed during the production of this research, none whatsoever.